Hi, good morning, everybody. Welcome to this webinar of DevoTeam. We have a nice number of attendees in the call, so we'll just get started right away. So this is starting small with Google BigQuery. I'm your host, Marinus Snijman, and I'm joined by my colleague Cas, who will introduce himself shortly. So what we will be looking at this morning, this is the agenda. We'll give a bit of background information. So firstly, introduction of ourselves and DevoTeam. Then we'll look at the state of affairs at this particular customer and use case that we've implemented. And of course, we are looking at data warehousing solution of BigQuery that we have done. We will then go to a live demo of CAS that will show a little bit of more in detail of what we've done. And we will wrap up with a small conclusion, and we will answer questions. So in the webinar tool, there should be a place where you can ask some questions. So please type your questions in there during the webinar. And at this stage, at the end, questions and answers, we will go and answer of many of those as we can. So a little bit about myself. I'm Marinus Snijman, Senior Consultant at DevoTeam Netherlands. I have 15 years of experience in areas such as enterprise application integration, software development, data analytics, and cloud. I am also the community lead for data here in the Netherlands, and I'm a certified Google Professional Data Engineer. My details are also here on the screen, email and LinkedIn. Feel free to use them. And then my colleague Cas can introduce himself.
Hi, thank you, Marinus. Hi, everyone. I'm Cas Beuseminder. I've been at DevoTeam for about 1.5 years now, a bit more, as data analytics consultant, and I primarily work with data engineering, setting up data pipelines, and data warehousing. I am also a certified Google Professional Data Engineer.
Thank you, Cas. So a little bit about DevoTeam for those that don't know us. So we are a consultancy. We're in 18 countries, located in Europe, Middle East, and cloud. We have 7,800 digital transformakers, as we call ourselves. So that's of course employees with a revenue of around 800 million for 2019. And we have 3 global partners, which is Google, Red Hat, and Service countries, but we have some more partners locally in different countries. For example, AWS, Salesforce, and Microsoft here in the Netherlands, where we are, but also some more. Then myself and Cas are both here in the Data as a Service unit in the Netherlands, where we typically do implementations for data foundation, cloud data warehousing, and data analytics projects. And again, some of the partners that we work with, Informatica, for example, it was not on the previous slide, and a lot of the technologies that we work with. So many of the data technologies we work with. But of course, today we will be focusing on BigQuery and Google Cloud. So a bit of the state of affairs of the project or the use case that we have here. So here is a very big empty architecture diagram. So it's drawn out this big for a reason, which I'll come back to later. So, but this was the starting position of a project or implementation that we did. So what we had was a application database that's running on Google Cloud, and we are using the MySQL version of Cloud SQL. And behind this database, there is, of course, a whole big architecture, microservices architecture, using a whole bunch of Google Cloud components, which is not relevant for this talk. But of course, there is a lot of things that we use, but all of them store the data inside a Cloud SQL database. And then from there, we have set up a read. There was a read replica that is being used. So that is a feature of Cloud SQL, which with one tick box that you just check, you enable a read replica, where without any configuration needed, you get a replica of your database that you can use for reporting. And that was being done using Google's Data Studio. And the nice thing about this is that you don't impact performance of your application at all. So you can query, do all kinds of things on your database without worrying that you will slow down your users of your application. However, there was a couple of pain points with this solution that we started with. So firstly, one of the pain points was slow reports. So this is slow in terms of actually loading reports. So complex reports were taking up to 2 minutes to run. However, also slow in time to market. So we needed to have a developer for each new report to be created, which was not always best for business users. So yeah, that also led to data not being easily accessible. So it was difficult for business users to quickly gain insight into data. And the customer felt, many times we heard this term, that they are feeling like they're driving blind. And lastly, the solution was not really future-proof. So there were some discussions in the organization for initiatives to be coming soon, one of which was a machine learning project to be done together with one of the universities here in Netherlands. Another one was some requirements from more applications, financial systems and more, to also be included in the analytics and reporting, which was not really easy in this current state. So action was actually needed and quite fast. So we did not have a lot of time to implement this. So looking to a solution that we of course are doing here a lot, the Devo team, is a data warehouse. So here are some of the advantages of using a data warehouse. So of course there are many more, but these were the main advantages that were overlapping with our pain points. So firstly is speed. So data warehouses are built for performance regardless of the size of the data. So you can query huge volumes of data without having really slow query speeds. And another advantage is data model. So you can design and build a data model inside the data warehouse with business users in mind. So instead of having an application with a relational database, complex joins between different tables, maybe even a microservices architecture where each microservice stores its data in a separate database or schema, there is no way a business user will be able to look at a very complex model like this, or nor have the time for that. So in a data warehouse, you can create a nice model that is understandable by business users and create it specific for different domains or departments. Another big advantage is that you can combine multiple data sources. So many organizations now don't have just one application to report from or to do analytics from, they have multiple. So with the data warehouse, you can combine data from multiple applications into your data warehouse and have a single place where you do your analytics, reporting, visualizations, etc. from. And last but not least, of course, many of the more modern cloud data warehouses gives you ability to look at trends, do machine learning, and of course, for all of this, it uses historical data. So you can much easier in the data warehouse keep track of historical data for much lower cost and much higher performance than keeping all that history inside your database of the actual application. So these all were really overlapping with our pain points, and we saw, okay, we can quite reduce our pain points if we implement this. So obvious choice for us was Google's BigQuery. So the whole application and the whole landscape were already running on Google Cloud. So BigQuery was a obvious choice. It integrates very nicely with the rest of the tools. So yeah, BigQuery is basically a fully managed cloud data warehouse solution from Google. Some of its key points or features that stands out from others. One is that it scales seamlessly. So it automatically scales without you needing to do anything. It does that by decoupling compute and storage and scaling both of them independently. So that also helps with keeping pricing and the costs under control and scaling just where it's needed. Another standout feature is the machine learning that's built in. So you can quite quickly build and operationalize machine learning models directly in BigQuery. And it is really fast. So it has unmatched performance. It's best in industry and security for cost that fits your budget. So it's quite inexpensive, relatively speaking. And security also, the whole of Google Cloud has been GDPR compliant and also ISO 9001, which was a requirement from this particular customer. So it met all the security and compliance standards, even in very tough industry. So for us, it was really almost a no-brainer. So let's look at what is a typical implementation, and this is a typical architecture that Devo team might be using at customer, and we also have implemented many times. This is quite a big, so I'll show what we would typically do, but how we in next slide I'll show how we manage to keep it small for this particular case. But what you would typically have in implementation is you'll have some data sources. You might have an application that's inside Google Cloud, running on Cloud SQL, for example. But you might also have another application that you need to access data via API. It might run in different cloud, or it might run on premise. Or you might even have another application with legacy database, all kinds of ways to connect to that. So, and then typically, what we do is have the extract phase. So that's the first step, to extract the data out of the source data sources. And we would use either Cloud Functions or App Engine for that. Typically, we would use Cloud Functions. However, sometimes you need to use Google Cloud's VPN to connect. And at this point in time, it's not yet supported on Cloud Functions. So we would use App Engine, which is Google's managed Kubernetes service. And from there, you can also configure Cloud VPN to connect to other clouds like AWS, but also to your on-premise data center to have network connectivity between your source application or source data source and Google Cloud to extract the data from. And then after the extraction phase here, it will store the data on cloud storage. So how is this all triggered? Typically, you would use something like Cloud Composer, which is an orchestration and scheduling tool from Google, which you can do quite advanced things, manage dependencies between different flows, etc. For those that may be familiar, it's basically Apache Airflow, which is just the managed version, Google managed version of that. And you will kick off your jobs, and then you would typically use something like Cloud Dataflow as an ETL tool to transform the data and insert it into BigQuery. So again, Cloud Dataflow can handle very huge volumes of data. It has built-in scaling. It's quite an extensive ETL solution. And then once the data is in BigQuery, you can do your reporting as you normally would. So you can use Data Studio, or you might do machine learning on it with CloudML, or maybe you want to do some analysis with Cloud Data Lab, etc. However, if you look at this is quite a lot to implement and quite extensive architecture. Also, something like a Cloud Composer needs several VMs which it runs on. Cloud Dataflow also is quite a lot that it needs to spin up. So for this particular case, we really wanted to start small because of limited budget, limited resources, limited development time. So we came up with something that is still a basis for this reference architecture, but much simpler. So what we've done is saying, okay, for now, we only want to connect to Cloud SQL database that's inside Google Cloud and its read replica. So we'll just use Cloud Functions. For this, we are using Python Cloud Functions. And instead of using Cloud Composer for orchestration triggering, we are using Cloud Scheduler, which is more basic, but is enough for our needs. So Cloud Scheduler is a cron style scheduling tool in Google Cloud. It uses the same notation as cron job, unique style cron jobs. So it's already familiar to us. And we are just scheduling the jobs to run every 24 hours or whatever the case is that's needed. And it's efficient. So very basic, very quick to configure. We trigger that then via PubSub. So that's just the messaging to trigger the tools. And the Cloud function, of course, then extracts the data and inserts it directly into BigQuery. And then from BigQuery, we've now moved all our Data Studio reports to, instead of how it was before, Data Studio was connecting directly to the Cloud SQL database, it now connects to BigQuery instead. In addition to Data Studio, we've also introduced reporting in Excel via the BigQuery ODBC connector. So I'll come back to this later, but this is really, really useful for some finance users that rely heavily on Excel and want to continue using their existing macros and pivot tables, etc., that they have currently in Excel. So if you look at what we started off with, this picture, you can see it adding a little bit more complexity, but not that much. It's still relatively simple and still can be implemented in quite a short amount of time, yet the value it adds is quite big. So that being said, I'll hand over to Cas to give a live demo of how we have implemented this.
Yes, thank you, Marinus. Marinus, can you? Yes, thank you. Okay, I will give a short demonstration of the architecture as Marinus has just explained. To start with, in a MySQL server in Cloud SQL, I've generated some sample data, which includes about 34,000 rows of customer data. That includes extra information such as the categories that they're interested in and cities that they live in. This is a relatively small data set with not too many rows and not too many joins. However, already you can see that occasionally it takes 1 to 2.5 seconds to run. If the data were to be relatively larger or more complex joins or more joins, this would quite quickly become quite a long time to wait. That's okay if you occasionally want to extract data, but if you want to work with the data in a bit more interactive fashion, waiting a few seconds every time or more is not necessarily desirable. Secondly, this has the problem that it needs SQL syntax, and especially with larger, complexer joins, you would want someone who is comfortable with SQL to write these, and those aren't necessarily the people that have the best insight in the business, and those are the people that you want to be able to use the information. So instead of this classical normalized SQL table, we instead want a relatively flat BigQuery table, which has all the information exactly where you want it in one table with human readable names in a format that the actual user, the business user, can understand and make use of. This is an example table of the same data in BigQuery that runs currently in about a second. It has the benefit that it will basically always run in this time, no matter how large you scale it. Because all the joins have already been done, that is also not a concern. So this is a speed that you can expect no matter what size you are working on. This also has all the information that a user might want in a format that a user might want to make use of. As Marinus already explained, we're using Cloud Functions, the serverless compute service of Google Cloud, to get the data from Cloud SQL, transform it, and put it into BigQuery in this format. We have the following function for that. First of all, this function gets the SQL data and BigQuery data and connects to the databases. Afterwards, it does a check to see at what point in time the BigQuery data was latest updated. When was the last change made to the BigQuery data? After all, in the SQL data, we only need to see and introduce the new rows that have been changed or added to the SQL database after the last time that data was added to BigQuery. Everything else is already in BigQuery and we don't need to concern ourselves with for inserting into BigQuery. So with the function, we see when is the last time that a change was made in BigQuery. After this, making use of a separate file that includes all the queries, we extract the data that we want from SQL and load it into the Cloud Functions. This is in essence also the transform part of the Cloud Function, because it gathers the data from SQL in the formats that we might want it in BigQuery. This data is then inserted into BigQuery in blocks. BigQuery has a limit for its insert function of a few thousand rows, approximately 10,000, more than that, and it gives an error that the size is too large. Because of that, we've cut it up in blocks and insert an X amount of blocks so that all the rows are inserted. This ensures that all the rows that have been added or changed in BigQuery in SQL are now also correctly in BigQuery. However, BigQuery recommends that instead of updating or deleting, you instead just append the new rows and then find a system to only show the most up-to-date and accurate rows to the end user. To do this, we have two things. First of all, a delete check, where we check for every ID in BigQuery whether that ID is still present in BigQuery. Is still present in SQL. If your SQL database has hard deletes, then occasionally rows get deleted without a trace, and we would need to find out for every row in BigQuery whether the row is still in the MySQL client. It's quite a straightforward task where we query every unique ID in BigQuery, every unique ID in MySQL, and see if there's IDs in BigQuery that are not in MySQL. If they are, we insert a new row with that ID, and in a separate column, the value deleted to indicate that it is in fact deleted and should no longer be shown. The deleted column normally has null value for rows that are still active. Secondly, we have a system where we create a view that for each ID only shows the latest version. We do this using views. I can probably show you the syntax for this, where for every table and for every ID, we iterate over every row number to assign them a number, where the most recent version of each ID gets a 1, and then afterwards 2, 3, etc. From the raw data, we only select those tables that are most recent, and of those most recent IDs, only the ones that are not deleted. So this view in essence provides all the information that is accurate, up to date, and still active that you want your users to use. However, we have found that in practice, these views occasionally are quite slow because it needs to partition all the data over row numbers and then select the ones that you want. Instead, every day when this Cloud Function runs, we create a table that copies the table of the view. Especially with how cheap storage is in BigQuery, this is essentially no extra cost for a lot of benefits in performance. A week ago, BigQuery actually added materialized views itself, which is the system that we're trying to emulate, as a beta. And we're currently experimenting with it, what the benefits are of actually using BigQuery's materialized view syntax versus the system that we've been using. So this Cloud Function, in essence, takes the data that we want to insert from SQL, transforms it into the format that we want into BigQuery, and then inserts it into BigQuery. Secondly, it checks are the rows in BigQuery still accurate and not removed, and only shows the business user the data that they should need to see. This Cloud Function through Cloud Scheduler, as Marine has already said, is triggered every day at 8 in the morning. We looked at the business when they would need the data. Updating it once every day was enough, and 8 in the morning seemed like a sensible time so that every morning they would have up-to-date data. Okay, so that's how we get the data in BigQuery. From BigQuery then we can start doing reporting and analysis. For this, we have, for this client, used Data Studio, which is a free visualization tool of Google. And as you can see here, we have a dashboard with visualizations and analysis of the data in BigQuery. Because of the relatively quick speed in BigQuery, you can also make interactive charts that are fast enough to provide results for specific categories or demands or questions that you have with it. It is extremely straightforward to set up such a dashboard. I will demonstrate that. You can simply click that you want to add a data source, go to BigQuery, and from that, select the project that you're working in, select the table that you want, select the data that you want, and add it. We add it to the report, and then from that point on, you can just insert whatever tables or visualizations that you might want. So that's how you build a Data Studio report with it. For the business, they also had a lot of Excel specialists that ideally would like to be able to work and just play with the data themselves to quickly answer the questions that they have in a tool that they're familiar with. And luckily, BigQuery also has a way to connect the data in BigQuery to Excel. It does that using a ODBC connector that I here have an example of. You can either just go to the project and the data set and the table that you want and load it from there, or alternatively, you can run a query that provides specific information that you might want. In the case of the business, to once again avoid SQL dependency, we just have a few pre-written statements that they can enter to get the data that they want. As you can see, this will load the data. And then anyone who has competence and experience in Excel can work with the data from BigQuery, which refreshes automatically and updates automatically in a format and system that they are used to. I think that is it for the demonstration, so I shall now give it back to Marinus for final remarks.
Okay, thank you, Cas. Let me make it full screen. Just a reminder, if anybody has questions, they can type it into the questions part in the tool. So let's thank you for that, Cas, again. So let's wrap up. So we can look at some pain points we had and what improvements we were able to achieve. So firstly, we said we had slow reports with complex reports taking up to 2 minutes to run, and new reports require the developer to be created. So after this implementation, reports are instant. All reports load in sub 1 second, irrespective of how much data there are. And in addition to that, many easier reports can be created without a developer. The second pain point we had was data was not accessible. However, now with the ODBC connector for BigQuery, business users can easily access critical data themselves with Excel. Actually, this feature has become really useful in the COVID times, where a lot of financial data was needed, kind of reports and analysis that is not typical. So there's no standard reporting, no standard data studio report, out of the ordinary analysis needs to be done. So, can connect to Excel and do everything from there. So very, very useful and a big improvement from what we had before. And our last pain point that we felt it was not really future-proof. So on that, we actually already implemented a research proof of concept where we have looked at BigQuery machine learning and compared it to AutoML tables on some machine learning initiatives we have. So both of them, of course, BigQuery ML uses BigQuery, but also AutoML tables, another product of Google. Even though it does not require BigQuery, it is very useful to use BigQuery as the source of your data and also have all the historical data in there. So, and this proof of concept was already a success, and we are looking forward to doing more with this. And that being said, all of these improvements was done in just a couple of weeks. Of course, we are building more on top of that and adding additional features and gradually moving towards the full-on architecture. but with a quick, very fast implementation, we were already able to give quite some benefits to the users. So that being said, I think I will go to questions if there are any, and it seems like there were no questions. So that means we did a really a good job showing everything. So that is it then. So if there are no questions, thank you for everybody joining. If you think of any other questions or would like to contact us for anything else, feel free to contact either Melle Schaap, our business development lead, or myself, or Cas if you have more technical questions or any other questions about BigQuery or other data warehousing solutions we have implemented. That's it then. Thank you very much for everybody for joining, and we'll see you next time.